the last class, we were working out the various components of the angular momentum in a spherical polar coordinate system, and I had explicitly worked out what Lz was in a spherical polar coordinate system, and Lz turned out to be minus I h cross del by del phi, and I had asked you to also work out what Lx and Ly are in a spherical polar coordinate system. Then we had started out to calculate L squared, the operator L squared in the spherical polar coordinate system. So let us work out what the operator L square is in a spherical polar coordinate system today. So let me show you Lx, Ly, Lz again, Lx, Ly, Lz, and the operator L square is equal to Lx squared plus Ly squared plus Lz squared plus Lx squared plus Ly squared. So we have to square these three operators and add them up. We had set out to do this in the last class, so let us start afresh and finish it off today. So the first term, Lz squared, gives us each of these terms has a I h cross outside. Irrespective of whether there is a minus or plus sign, when I square it, I get minus h cross squared. So I can put a minus h cross square, overall minus h cross square outside. Then if I square Lz, then I get del by del phi squared. This is Lz squared. Now let me write down the various terms corresponding to Lx squared. So there will be one term which is the square of this operator. There will be one term which is the square of this operator, and there will be one term which is the product of this operator acting on this operator, and another term which is this operator acting on this operator. So let me write down these four operators over here. So the first term is sine square phi del del theta square. So we have sine square phi del by del square theta. The second term is the square of this operator. So the square of this operator, if you look at it, the del del phi, when I square this operator, del del phi will act on cos phi, but cot squared theta will remain unaffected. So I can put a cot squared theta outside plus cot square theta, and then I have cos phi del del phi acting on cos phi del del phi. This is the second term. Now we have the cross terms. So the cross terms, there are two cross terms. The first cross term will be when the product of these two operators. Del del theta will act only on cos theta. So I have one term which is sin phi cos phi, sin phi cos phi del del theta acting on cot theta del by del phi, and I have one more term which is this operator multiplied with this operator. Del del phi will act only on sin phi, so I have cot theta plus cot theta cos phi del del phi sin phi del del theta. So these are the four terms which arise from Lx squared. let me also calculate Ly squared. So Ly squared will have one term which is cos square phi del square del theta square. So let me put that down first. So I have a plus sign here, and I have cos square phi del by del square theta. Then I have the square of this term. Here again, del phi will act only on sin phi when I square this, rather will act on sin phi. So I have plus cot square theta sin phi del phi. Then I have sin phi del phi. Now I have the product of this with this, and del theta will act only on cot theta. So I have minus cos phi sin phi del theta cot theta del phi, and I have the last term which is this acting on this. So I have minus cot theta sin phi del by del phi cos phi del by del theta. So this is, let me put a square bracket here to avoid confusion. So this is the whole thing. And this can be now simplified. So let us see which of these terms cancel out and which of them remain at the end of the day. So del by del square phi doesn't cancel out with anything else here, and del by del square phi, let us see if there is any other term. Okay, let me just put down the terms, that will be simpler. So now let me put down the terms one by one over here. L square is equal to minus h cross square, and the first term passes through unscathed, del by del square phi. Now sin square phi del square del theta square, and here we have cos square phi del square del theta square. So we add up these two terms, we get just del by del square theta square. So we have plus del square del theta square. So let me mark the terms which have been taken care of. This has gone, this is gone, and this is gone. Now let us see if any of these terms cancel out. So this term over here, sin phi cos phi del by del theta cot theta del by del phi, cancels out with this term which is exactly the negative of this. So this is also taken care of. Okay, so these two terms are gone. Let us see if any other term cancels out. So this has a cot squared theta, this also has a cot squared theta, but this has a cos phi, this has a sin phi. Now if we differentiate the cos phi, we get a minus sin phi. If we differentiate the sin phi, we get a cos phi. So if you differentiate this term, if del by del phi acts on cos phi and del by del phi acts on sin phi over here, these two terms, the resulting terms, are going to be just the negative of each other, and they will cancel out. So the only term which will not cancel out here will be when del by del phi goes through over here, and you will have del by del square phi. So what you have is cot square theta into cos square phi del by del square phi, and here you have cot square theta sin square phi del by del square phi. So these two terms contribute to give me plus cot square theta del by del square phi. Okay, because when this acts on the cos phi, it cancels out with the term which I get when this acts on sin phi. So these two terms are taken care of, and what remain are only these two terms over here. So let us see what the outcome of differentiating this is. So if I differentiate this, then I have, okay, if del by del phi acts on sine phi over here and del by del phi acts on cos phi over here, what does it give us? Let us see that. So when del by del phi acts on sine phi, it gives us cos phi. When del by del phi acts on cos phi, it gives us sine minus sine phi. So we have cot theta cos square phi, and here we have cot theta sine square phi. We get another plus sign, overall plus sign. So what we have is cot theta into del by del phi, because cos square phi and sine square phi give us 1. So the resultant of the sum of the two terms when del by del phi acts on sine phi and del by del acts on cos phi over here, the resultant of these two terms is plus cot theta del by del theta. There is one more term when del by del phi just goes through without acting on this, which will be a double derivative term, but that term will cancel out because I have cot theta cos phi sine phi and cot theta cos phi sine phi, but the signs are different, so that term will cancel out. So we have taken care of all the terms here, and the result is there in the is now this. So this is the operator L square in a spherical polar coordinate system. Let us simplify it further. So L squared is equal to minus h cross squared. Now del square phi, so the coefficient of del by del square phi is 1 plus cot square theta and these two terms can be combined and written as follows: 1 by sine theta del by del theta acting on sine theta del by del theta, because if we differentiate sine theta we get cos theta, which gives us the cot theta term, and we just have one derivative with respect to theta. And if I don't differentiate sine theta, but then I get del square by del theta square, and the sine theta cancels out. So this is finally equal to minus h cross squared. This is 1 by sine squared theta. So I have 1 by sine squared theta del by del square del theta square, del phi square, plus 1 by sine theta. Okay, let me write it. Now, so this is what we had set out to calculate, L square in a spherical polar coordinate system. Now let us go back to the problem we had started out with. We were looking at the Schrodinger equation for a particle in a three-dimensional potential, and this problem we had separated into two parts. One part was the radial part, and the other part was the angular part. We had used the separation of variables to separate this problem into two parts. So the Laplacian operator del square, if we write it in a spherical polar coordinate system, it turns out to be this. Well, the radial part over here is wrong. It will be slightly different, but it doesn't make a difference as far as this discussion here is concerned. So there is a radial part, some radial operator which acts on f. The expression given here is slightly wrong. I will rectify it when we come to it. Yeah, so we will do it. We will rectify it when we come to it. We don't require it right now. And there is the angular part, which only acts on the theta and phi dependence of the function. And the angular part we had written as some operator omega into f, where this 1 by sine theta del by del theta sine theta del by del theta plus 1 by sine square theta del square by del phi square was denoted by the operator omega. And using this operator omega, we had then been able to separate the equation into two different equations, the Schrodinger equation into two separate equations, one for the radial part and one for the angular part. And we found that the angular equation has to satisfy, the angular part has to satisfy this equation, omega acting on some function y of theta and phi is equal to some constant into y. Now, so this was how we had reduced the Schrodinger equation for a particle in a spherical polar coordinate, in a spherical potential into two separate problems, a radial part and a part which depends only on the angle. And the angular part had this operator omega. Now, here we have started from the angular momentum operators. If you convert the angular momentum to operators in quantum mechanics, and then if you calculate L squared, the square of the angular momentum operator, then we find that it comes out to be equal to, L square comes out to be equal to minus h cross square into the same operator omega, which appears in the problem of the Schrodinger equation for a particle in a spherical potential. Okay. So this is the first point I would like you to note. So the solution, the solving the Schrodinger equation for a particle in a spherical potential then reduces to solving this equation L square, omega is L square by minus h cross square. So this is equal to minus L square y is equal to minus h cross square c y, right, because the operator omega is L square by minus h cross square. So this equation, the spherical, the angular part of the Schrodinger equation is the same as this equation over here, which basically tells us that these functions y are also eigenfunctions of the angular momentum operator, not the square of the angular momentum operator. Okay. So this is the first point I would like you to note. So the square of the angular momentum operator appears naturally in this problem of a particle in a spherical potential well. How does this square of the angular momentum, let us also look at the Schrodinger equation, the Schrodinger equation or the Hamiltonian. So I have already also told you that the classical Hamiltonian can be written as the yes. So I have already told you that the classical Hamiltonian in a spherical for any particle in a three-dimensional potential can be written as 1 by 2m the radial momentum squared plus the angular momentum squared by r squared plus the potential. This is the classical Hamiltonian. So in quantum mechanics, the corresponding operator right? And the angular part of the Schrodinger equation comes about from this L squared. This, the operator corresponding to the radial momentum is just the radial derivatives, involves just the radial derivatives, and it is the angular momentum squared, L squared term, which gives us the derivatives with respect to the angular coordinates, and the separation of variables method separates these two parts into two sets of equations. Okay. So the angular dependence of the wave function for this is basically just the solution of the angular momentum problem. So we have to in order to study this problem, we have to basically look at the angular momentum problem. We have to look at the eigenfunctions of the angular momentum squared, the operator L squared, and those are the angular part of this wave function. Okay, so that is the reason that is the reason why we have started looking at the angular momentum operators. So this is the first point. The second point I would like you to note is as follows. We have worked out the commutation relation between the various components of L. We find that the different components of L do not commute amongst themselves. Right, this is not equal to 0. But all the components of L commute with L squared. Now, let us study an implication of this fact. Let us study two implications of this fact. The first implication is as follows. Let us look at the time evolution of the expectation value of the angular momentum. So suppose I have a wave function psi which describes the state of the particle, and psi will be evolving in time, and the time evolution can be calculated using the Schrodinger equation. Now the question I would like to address is, how does the expectation value of any component of the angular momentum, let us say Li, or any operator, any physical quantity, evolve in time? So we want to look at how this evolves in time. So we want to look at this. Okay. How does the expectation value of a particular component of the angular momentum evolve in time? So let us work out this quantity. So this is equal to d by dt, and here we have the integral psi x t, psi star x t, Li psi x t d cube x and this is equal to del by del t psi star. I am not showing the arguments explicitly anymore. So we have one term which is del by del t of psi star Li psi d cube x plus psi star Li del by del t of psi d cube x. Now del by del t of psi, we know what this is. We know that I h cross del by del t of psi is equal to the Hamiltonian operator acting on psi. If we take complex conjugate of this, then we know that I h cross del by del t of psi star is equal to h dagger of psi star, but h dagger is the same as h. So there should be a minus sign here. So we can use these two in this to calculate how the time derivative of the expectation value behaves. So let us do that. So what this gives us, del by del t of psi star, is that this is equal to I by H cross into I by H cross into the Hamiltonian acting on psi star. Okay, let us put it. Okay, this. Let us keep it like this, the Hamiltonian acting on psi star, and then I have Li acting on psi d cube x. Yeah, so this will be just a psi star over here. I am just taking complex conjugate of this equation, and then I have plus minus I by H cross psi star Li acting on H psi d cube x. Now, from the definition of Hermitian of the dagger operator of the conjugate, the dagger operator, this is equal to, I can take the I by H cross outside, psi star H Li dagger. This should be a dagger here, but the dagger of H is the same as H itself. So this is equal to this acting on psi d cube x with the minus sign here. No, sorry, the minus sign will appear here with the minus sign I by H cross, and here I have psi star Li H psi d cube x. So what do we get? We find that d by dt of the expectation value of Li is equal to I by H cross into the expectation value of the commutator of H with Li. This is nothing but the commutator, because I have HL minus LH. So this is nothing but the expectation value of the commutator. So we find that the expectation value of Li evolves, the rate of change of this is equal to I by H cross into the expectation value of the commutator of the Hamiltonian with the angular momentum. Now this is very similar to the equation of motion in classical mechanics. If you have done a sufficient amount of classical mechanics, in classical mechanics you will encounter exactly a very similar equation. The equation in classical mechanics for angular momentum, or for this equation holds for any observable quantity, not only angular momentum, for any observable quantity, its expectation value evolves exactly in the same way. The classical equation in for the angular momentum operator will be d by dt of not for the angular momentum, will be equal to the Poisson bracket. So in classical mechanics there is something called the Poisson bracket, which you might or might not have encountered, but the corresponding equation in classical mechanics is this. So the evolution in quantum mechanics is exactly analogous to the evolution in classical mechanics, except that you have to introduce the expectation values and I and H cross. Okay. So let us not bother about this, since you might not have encountered the Poisson bracket till now, but let us work with this. So this tells us how the expectation value of the angular momentum operator evolves with time. Now for a spherically symmetric potential, the Hamiltonian is given by this. Now the angular momentum operator L commutes with the radial component of the momentum, because the angular momentum operator L involves only derivatives with respect to theta and phi. Right? We have just worked out what L is in a spherical coordinate system, and we see that the different components of L, Lx, Ly, Lz, all of them involve derivatives only with respect to theta and phi. Now in the Hamiltonian we have two terms. We have p radial squared, the radial momentum squared, and we have the angular momentum squared. The radial momentum involves only radial derivatives. So this obviously commutes with all components of the angular momentum. We have also seen that L squared commutes with all components of the angular momentum. So the commutator, and this also involves only the distance, so this also commutes with all components of the angular momentum. So the commutator h into the angular of h and the angular momentum is 0. So this is exactly equal to 0. So what this tells us is that d by dt of the expectation value of any component of the angular momentum is 0. In classical mechanics, we know that if a particle is moving in a spherically symmetric potential, its angular momentum is conserved. The analogous law over here is also the conservation of angular momentum. The quantity which gets conserved in quantum mechanics is the expectation value of the angular momentum. Okay, so this is the fact that angular momentum is conserved. So this is not only true for angular momentum. In classical mechanics, any quantity whose Poisson bracket with the Hamiltonian is 0 is conserved. Okay, or you may say that any conserved quantity in classical mechanics, the corresponding fact in quantum mechanics will be that the expectation value of that quantity is conserved. It remains constant as the particle evolves. Okay, not only for angular momentum, but for any quantity in classical mechanics which is conserved, you have the similar kind of fact in quantum mechanics. So this is one direct consequence of the commutation relation between these angular momentum operators and L squared. Now let us look at another consequence of this fact. The second consequence arises from the fact that the different components of angular momentum do not commute. All of them commute with L squared, and as a consequence, the expectation value is conserved in a spherically symmetric potential, but they don't commute amongst each other. Now, if we ask the question, can I have an eigenfunction, set of eigenfunctions, which are simultaneous eigenfunctions of Lx, Ly, and Lz? The answer is no. You cannot have a set of eigenfunctions which are simultaneously eigenfunctions of all three components of the angular momentum. This arises from the basic fact that if two operators do not commute, let me write down the basic theorem. If two operators do not commute, it is not possible to have a set. By set I mean a complete set of eigenfunctions for which are set of functions, let me put functions, which are simultaneous eigen functions of both. Okay. So let us say that there is one operator A and there is another operator B, and the commutator such that AB is not equal to 0. The commutator of A and B is not equal to 0. Let us suppose that there exists a set of eigenfunctions, complete set of functions, which are simultaneous eigenfunctions of both A and B. Let us call it psi, let us label them like this: psi A1 B1, psi A2 B2, psi A3 B3. So these are a set of functions such that if A acts on psi A1 B1, it will give me A1, and if B acts on it, it will give me V1. Etc. For if it acts on A2 B2, then this will give me A2, and if B acts on psi A2 B2, it will give me B2. Okay. Let us suppose that there exists such a set of complete set of functions. Then any arbitrary wave function psi can be expanded in terms of these. If such a complete set exists, then any arbitrary wave function can be expanded in terms of this. So we can expand any arbitrary wave function as Ci psi ai comma bi, right? This just follows from the fact that they form if such a basis exists, a complete set of such wave functions, then you should be able to expand by the definition of completeness. Now let us work out what is the commutator of this acting on psi. Then this will be equal to, so the commutator is AB minus BA, and this will act on some Ci into AI comma Bi. Now when B acts on this, it will give me a number Bi. The state remains unchanged, the wave function remains unchanged, and then when A acts on it, it will give me AI. So this will be equal to AI Bi minus Bi AI and it will be equal to 0. So for any wave function, if the commutator of A and B acts on it, it gives 0. But I have already assumed that the A and B don't commute. But if the commutator acting on any wave function is 0, then we have an inconsistency. A and B don't commute, but the action of the commutator A and B on any wave function is 0. There is an inconsistency, which tells us basically that this is not possible. You cannot have such a complete set of eigenfunctions. You may have 1 or 2 or 3, whatever, a finite number of such eigenfunctions, which are such functions which are simultaneously eigenfunctions of A and B, but they cannot be a complete set of eigenfunctions, because if they were a complete set, then you could expand any wave function in terms of these, and then the commutator would have to be 0. Okay, so we have just proved that you cannot have simultaneous a set of eigenfunctions for two operators which don't commute. So what this implies is that you cannot have simultaneous eigenfunctions of, so it is not possible to have simultaneous eigenfunctions of Lx, Ly, Lz. So one eigenfunction, a set of eigenfunctions can either be eigenfunctions of Lx or Ly or Lz. Okay. So let us, we have to choose one of them and work with it. So let us choose Lz. Okay. So we are going to work with eigenfunctions of Lz, the operator Lz, and the direction z can be chosen arbitrarily. It is up to us to choose which is the z direction, because the problem is spherically symmetric. So we can choose some arbitrary direction to be the z direction, and we shall work with the eigenfunctions of the component of the angular momentum in that particular direction. So let us, so we are going to work out eigenfunctions of this, and these eigenfunctions, let us say that we have some constant C1 is equal to C1 into psi C1. Okay, C1. Or no, C1 we have, okay, doesn't matter. C1 into, or better to use K, because C1 has been used in the expansion. Okay, so we are going to solve this equation. Now, okay, because the C's have been used as expansion coefficients for the wave function. So these psi k's are defined to be eigenfunctions of Lz. L squared commutes with all three of them. So this psi k will also be an eigenfunction of L squared. So this will be also an eigenfunction of L squared, and it will give us some number. So this number could be, let us say, C. Okay, I can have simultaneous eigenfunctions of L, and it should be C by minus C by h cross square for consistency. Okay, so these wave functions psi, or they have been actually denoted by y earlier, so we can switch over to y. So we want to work out a set of eigenfunctions which are simultaneous eigenfunctions of Lz as well as L squared, and they will not be, the whole set of eigenfunctions will not be also eigenfunctions of Lx and Ly. Now what is the physical implication of this? Suppose I make a measurement of the z component of the angular momentum. I have a particle in some arbitrary state. I make a measurement of the z component of the angular momentum. Once I make a measurement of the z component of the angular momentum, it will go into one of the eigenfunctions of the Lz. Now these will not be eigenfunctions of Lx and Ly. So once, if I know the Lz, the z component of angular momentum precisely, then I will not have precise information about Lx and Ly, because these are not eigenfunctions of Lx and Ly. So if I make a measurement of Lx now, I cannot in general predict what value I should get precisely. Okay, so these will be superpositions of eigenfunctions of Lx and Ly, and I can only give probabilities for different values of Lx and L, of Lx, let us say, if I make a measurement of Lx after I have made a measurement of Lz. So this gives us some uncertainty relation between the values of Lx and Ly, Ly Lz, or Lz Ly. Okay, because I cannot precisely fix the values of all three of them, because I cannot have simultaneous eigenfunctions of all three of them. Okay, so we are brought back to the uncertainty relations once more. We have seen that the wave nature gives us forces us to have some uncertainty between the position and momentum. Here again we find that there is some uncertainty between the different components of the angular momentum. The uncertainty relation is basically a consequence of the commutation relation. If some operators don't commute, then there will be some uncertainty relation between the expectation values of these quantities. Okay, and the exact relation we shall derive later on in the course. But you should keep in mind that there are uncertainty relations between the expectation values of L square, Lx square, Ly square, and Lz square. So for today we shall stop here. In the next class we shall work out the eigenfunctions for the set of operators Lz and L squared. So are there any questions you want to ask? Have you encountered the Poisson bracket in classical mechanics? Oh, you have encountered it. So you know the equation of motion also, right? What is the Poisson bracket equation of motion?